Great. Let's continue then talking about the alternating series test. I gave you like a little introduction last time. This time we can do a bunch of examples. So this is the alternating series test. And it says if you have a series like this, that is some kind of a series where the signs are alternating and then you have some other stuff. So this minus 1 to the n there makes alternating signs. And then you have some other stuff, the bn, right? So in this case, if two things have to be true, and then this will converge. It's the two things are, first of all, bn plus 1 less than or equal to bn. That is to say, it's decreasing. Although not strictly decreasing, it can be less than or equal. It doesn't have to be straight up less than. And so these two things both must be true. Lim bn n goes to infinity equals 0. Then the series converges. This is the alternating series test. All right. This is how you show that an alternating series converges. Can you read what I said there? Yes? All right. So this is the alternating series test. And the idea behind this is you're adding up a bunch of things, but they are alternating in signs. So for instance, like a very important example like this would be something like 1 minus a half plus a third minus a fourth plus etc. So this is called the alternating harmonic series, and it if you write it as a formula, it's this minus 1 to the n times 1 over n, right? This one actually does converge because the both of those two things are true of it's decreasing and also the limit is 0. We'll go through that, but why should you believe that this actually converges? The idea is if you're trying to add all this stuff up, if you I'll try and sort of draw the answers, what you get if I was to add these numbers up. If you just take the numbers one at a time, the first number is 1, so that's over here, right? And then I add negative a half, which pushes me back a little bit to here, and I end up getting 1/2. That's if I just add the first two of them. You start at 1, and then you subtract a half, so you go back here. But then the next one you add, so you move like to the right a little bit on the next one. And then you move to the left a little bit again on the next one, and to the right again on the next one. Because it's alternating, these things, as you add them, they keep on bouncing back and forth. And if those things that you're adding are also getting smaller every time and becoming 0, that means these little bounces back and forth every time, those little bounces get super small, and that means you're eventually going to stabilize at a particular value, which is the answer. All right, this is just a very vague picture trying to describe why you should believe that these two things are necessary, or they make it converge, right? If these values that you're going back and forth each time, but they're getting smaller every time and going to 0, that means that it's going to converge. All right, so let's try this very specific example. This is a very easy one, but how about show that this converges? And I want to try and write this out in detail using the alternating series test. All right. There are two parts, and we have to demonstrate each of the two parts. So we need to show the two parts. They are, decreasing and the limit part, right? The first one was that the terms are decreasing, and the second one is that the limit of the terms equals 0. And now it's important to, a little technicality here. When we write this sequence, what are, if you look in the box that I wrote before, these b's is what I'm talking about in terms of the b's have to be decreasing, and then the limit of the b's has to be 0. What are the b's? Notice that in the original series, you have the signs, the plus minus signs, and then the b's. So actually, in this case, The b's are just these numbers, not including the signs. All right, so in this example here, bn equals just 1 over n. You do not include the alternating signs as part of the b's, because in the original statement in the box up here, the sign is not part of the b's, right? So the bn is 1 over n. Let me just say the bn doesn't include the plus or minus sign. All right, it makes the b's a lot easier to deal with. What's kind of sometimes hard to deal with is the fact that there's this plus or minus sign. But the great thing about the alternating series test is that you don't have to work with the alternating part. You only have to work with the sort of those numbers, not their signs. Okay, anyway, we got the two parts. So I am going to do the decreasing part first. And this, I hope everybody remembers how to show that the series is decreasing. So I want to show that bn plus 1 is less than or equal to bn. And this we do the way that we did this, a couple weeks ago when we talked about showing that a sequence is increasing or decreasing. You can basically plug stuff in, simplify the inequalities, and hopefully at the end you'll end up with something which is obviously true. So that's what I'm going to do. So I'm going to say what I want to show is plug in here bn plus 1 is the same as bn. Well, bn is just what it is. It's 1 over n. I said up here. This is what bn is, 1 over n. And then what's bn plus 1? It's 1 over n plus 1. You just replace the n by n plus 1. All right? That's what I want to show. And then we can simplify this. In this case, those are two fractions. We can just multiply the denominators across. Make sure you keep the inequality sign going in the proper way. So what I'm doing in this step is multiplying this n onto the other side and then multiplying this n plus 1 onto that side. So this is the same as n on the left less than or equal to n plus 1 on the right. And that's true, right? N is, in fact, less than n plus 1. So this is true. All right, and so we have shown the decreasing part. That's one part of the alternating series test. The other part is about limits, right? So that was the decreasing part, and now the limit part. We have to show, remember what it said in the box, the other thing. One is this decreasing bit, the other thing is this. Lim n goes to infinity bn has to equal 0. And that, in this example, is pretty easy. I say lim n goes to infinity of bn, and I just simplify this. You better get 0 or else you messed it up somehow. It didn't work if you don't get 0. So this is an easy example. bn is just 1 over n, so that really is 0. Right? The lim n goes to infinity of 1 over n really is 0. Now, in a more interesting example, you might have to do some other, tricks or whatever to find that limit, but this was an easy one. All right. Any thoughts about this one? This is a very straightforward example of alternating series test. All right. So the moral of the story is the alternating harmonic series, that's what this is called. 1 minus a half plus a third minus a fourth, etc. converges. All right, I don't know if that's a surprise. It's interesting contrast with the harmonic series with all pluses. That one diverges. That one goes to infinity. But this one, if you're alternating this, the signs, so I will just say, remember, 1 plus a half plus a third plus a fourth. If they're all plus, that diverges. But if you alternate the signs, then it converges. Kind of interesting, in my opinion. What does it converge to? Again, actually, our tests or whatever are not sufficient to tell you what it converges to. That it only tells you that it converges. All right. We will eventually talk about what this converges to. You may be surprised. It converges to a very strange, although not too strange, but mysterious answer, what it adds up to. All right, great. Let's do some more fancy examples. How about, yeah, I got one more, and then I got one for you all to try. And then we can talk about our next business. Okay, how about show that this one converges. This one is alternating also. But this time, instead of 1 over n, this is looking like 1 over powers of 2, right? Here is 2 to the 1, here is 2 to the 2, here's 2 to the 3. So this one, if I were to write it as a series, it would be minus 1 to the n minus 1. You need this n minus 1 here because the first sign is a plus sign. And so we should, if you use just n here, then the first one will be a minus. Anyway, and then times the terms here are 1 over a power of 2. This is 1 over 2 to the n minus 1. Again, this is n minus 1 here because the first one is 1 over 2 to the 0. And so you need to put n minus 1 so that those guys start with the exponent of 0. All right? Anyway, let's try to prove that this one converges. All right? This is your job. Show that it converges. You do the 2 steps. There is the decreasing and the limit. And each one by themselves should work out fairly well. What's the Bn in this case? Remember, the Bn is what you see inside the sum, not including the signs. So the Bn in this example is this, 1 over 2 to the n minus 1. All right, and now I'm going to do the decreasing part. That one is, I want to show Bn plus 1 less than or equal to Bn. So this looks like, i.e., 1 over, well, this one over here is 1 over 2 to the n. This one is 2 to the n, sorry, it's n minus 1 on the right side and just n on the left side. Because I'm replacing n with n plus 1, I get just n. All right, as usual, we multiply across in this thing. So that means I want to show that 2 to the n minus 1 less than or equal to 2 to the n. All right, what can we do with that? Anyone got a suggestion? No suggestions? Yeah?
Maybe like take the log.
Take the log on both sides. This is not a terrible idea, although I'm not quite sure. Anybody remember the rule about what happens to the inequality sign? Can you just take the log on both sides? The answer is I don't want to get into that. It's a this is not a typical thing that you would do on an inequality like that. It turns out actually that is legal for specific reasons about the log, but I don't really want to get into that. Anyone have another idea? It's not a terrible idea, but those kinds of things, doing the same thing on both sides, of course, with an equal sign is always allowed, but with the inequality sign, you need to think hard about, do I need to reverse the direction or something else? For instance, you are not allowed to square both sides of an inequality. It'll mess it up unless you know something else. What do you? Anything else? Actually, you can simplify this just by dividing both sides by 2 to the n and canceling it. Anyone agree with me? Divide by 2 to the n here. Here's what I'm doing. Divide 2 to the n. The right-hand side gives me just 1. What about on the left side? You can divide both sides in an inequality by something, as long as it's positive, which it is. 2 to the n is positive. What do I get on the left side when I divide by 2 to the n? This would be like, I suppose I could write, I don't know if this helps, 2 to the n divided by 2 to the n minus 1, right? That's what I'm talking about. What is that? Oh, sorry, that's upside down. I'm dividing by 2 to the n. So it's 2 to the n minus 1 divided by 2 to the n, right? What is that? Any masters of, 7th grade algebra out there? There must be somebody. Yeah? 2 to the negative 1? Is that what you said? Yeah, it's 2 to the minus 1. Here I have 2 to the n up top, 2 to the n on the bottom, 2 to the n minus 1 divided by 2 to the n. What you should do, I suppose, is subtract the exponents. It's 2 to the power n minus 1 subtracting n. The n's go away and you just get negative 1. This is 2 to the minus 1, right? This is what, remember, this is what we need to show. Is that really true? Yes. 2 to the minus 1 is 1/2, right? And so it really is true. This is the same as 1/2 less than or equal to 1. And this is true. Right? That was painful. Bunch of steps. We can handle it. Okay, so it is decreasing. How about next? The other part was the limit, right? So we also have to do the second bit is taking the limit. That would be lim n goes to infinity. This one is also an easy limit. The thing I'm talking about is 1 over 2 to the n minus 1. And again, this just straight up is 0 because I have, when n goes to infinity, what I'm looking at is here is a fraction with an infinite thing in the denominator. All right. And so this is 0. All right, and there's not much to say about why it's 0. It just is because the denominator, if you like to say some kind of a reason, this is basically like 1 over infinity, which is going to be 0. All right. Those are the two parts, the decreasing and the limit. So that means that the sequence or the series that I'm talking about converges. All right, this is called the alternating series test. You show it's decreasing, you show the limit is 0. All right, I got one for you all that's a little more interesting to work through. So your job is to show that this thing converges. See what you think. Chat with your friends about it if you like. You should do 2 parts. I would say, like the one.
So
I mean, this one.
did you get 6 after or plus 6 squared? Minus 2 plus 6
Because all you care about is the part without the sign. Yes. So yeah, that matters. Still good here?
Would I like divide and try and like simplify that? But then the left side would be greater. So like the right side.
Yeah, you messed up something.
Okay.
All right, can we talk about these? I see a bunch of sort of like algebra hell going on with people trying to work out the first part. The limit part is quite a bit easier in my opinion, but let's just try to carefully go through the decreasing part. So first of all, Bn here is 2n over 3n squared minus 1. Actually, a lot of people, this is a good question. A lot of people asked as I was walking around, does it matter that this says minus 1 to the n rather than minus 1 to the n minus 1? The answer is it doesn't matter. The entire alternating series test is really about only focusing on this part. If this, the fact is, like, it's true, this is minus 1 to the n rather than n minus 1. The only difference between those two things, though, is that just like all of the terms, instead of being positive, they become negative. It doesn't affect whether it converges or not. It does affect what it actually converges to, but it doesn't affect what it whether it converges or not, which is all we care about. So it is okay to just sort of ignore the fact that this doesn't exactly look like minus 1 to the n minus 1. It looks like just minus 1 to the n. Anyway, that's my sequence. So I am going to do the decreasing part first. So I want to show bn plus 1 less than or equal to bn. This, when I plug in, I go 2n plus 1. You have to make sure that you are properly doing all of your parentheses where they go. Over here, 2n over 3n squared minus 1. Simplify here. On the left side, I need to distribute on top, and on the bottom, we have to do the FOIL. So this will say, this is the same as 2n plus 2 up top. On the bottom, 3n squared plus 2n plus 1 minus 1. This same stuff on the right-hand side. In the next step, I'm going to distribute the 3 and then subtract the 1. Do you mind if I do that at the same time? This says 2n plus 2 on top. Distributing the 3 gives me 3n squared plus 6n, and then plus 3. That's the last part of the distributing, but I have a minus 1 here, so I'm going to say plus 2 instead of plus 3, doing that subtraction by 1. I hope everybody's feeling good about this. 2n over 3n squared minus 1. All right, and now we multiply the denominators across, as we usually do in these kinds of things. This is the same as 2n plus 2 times 3n squared minus 1, less than or equal to 2n, 3n squared plus 6n plus 2. Finally, we do a bunch of more of distributing. On the left, I do the FOIL. This is 6n cubed plus 6n squared plus, minus 2n minus 2. I think that's what I get when I do the FOIL on the left. And then on the right is just a simple distributing 6n squared plus 12n plus 4n, n 12n squared, right? That's 2n times 6n, it's 12n squared. 2n times 2 is 4n. All right, how am I doing so far? I hope I'm doing okay. And then we can finally kind of cancel some stuff out. I have, I wrote, did I say squared? This should be cubed here. Did I say cubed and wrote squared? I don't know. Maybe I said it wrong too. Anyway, we are going to simplify this. I can, first of all, just straight up cancel those on both sides. What's left? I have 6n squared on the left, 12n squared on the right. Maybe I will put all the n's on the right side and leave the -2 on the left side. So this will say -2 less than or equal to, on the right side, I had 12n squared. I'm going to subtract 6n squared, so it becomes 6n squared. And then I had 4n on the right, and I'm going to add 2n, so it becomes 6n. This is what I was looking for here. This is what I want to show, all right? Any questions about that? I hope you ended up here. I saw some people messed up a step or two and ended up a slightly different place. But anyway, this now, I suppose you could divide everything through by 2, although it's not really necessary. This to me seems obviously true. Can anybody say why is that automatically true? -2 is less than that business on the right-hand side. Why is that true? Yeah?
Because the 6 is positive, so everything is multiplied by.
Yeah, because everything on the right you see is positive, right? N is positive, n starts at 1 and increases from there. And then I'm multiplying by 6 and adding. All of this is positive. So this is positive. So it is bigger than -2. All right, you should say something at least of explanation about why that's true. It's because the right-hand side is positive, but what we're saying is that it's greater than -2, and it is. All right. I hope that worked out for you all. Some people, almost everybody made some little mistakes in here. Unfortunately, if you make some mistakes, you will probably end up at a place where you can't say whether it's true or not. Here it's true though. All right. Okay, that was only half of this problem, although the rest of it is the easier part. We also need to do the limit part, right? That is, we have to show that, well, we have to find the limit n going to infinity of that thing again, 2n over 3n squared minus 1, right? You got to take this limit, and it has to be 0 in order for this whole thing to work. And this is a typical limit of the type that we've done before. You could either use L'Hopital's rule here, because you get something like infinity over infinity, or you could divide through by the highest power of n. That, to me, that's the more standard way of doing this. So I'm going to divide everything through by n squared. It'll say 2 over n up top, and then 3 minus 1 over n squared. This is dividing through everything by n squared. And then when I do this limit, everything with a little n in the denominator becomes 0. So this becomes 0 over 3 minus 0, which is 0 over 3, which is 0. And that's what we wanted, right? In that step, your goal is to show that the limit is 0. And that's what it is. You could have also done that using the L'Hopital's rule. All right. Any thoughts about this? I think the idea of this is not so hard. You just got to sort of execute it properly. Make sure you're not messing up anything in the inequality. That's the harder part. Any thoughts about it? All right. This is the alternating series test, and it is used to show that an alternating series converges. I have one little bit of caution here. Note, the alternating series test shows that it converges. It cannot be used to show that it diverges, though. So, to show it converges, you check the decreasing and the limit thing. If one or the other of those is false, that doesn't necessarily mean that it diverges, all right? So the alternating series test shows that it converges. To show it diverges, you have to just use some other method. And you may see some of this on the homework problems or on our quiz. I might show you an alternating series and say, you tell me if it converges or not, and then demonstrate it. If it converges, if you want to show it converges, you do this alternating series test. If you think it diverges, though, you have to just demonstrate that using some other method. So to show it diverges, you have to use another method. Unfortunately, like the other methods we've talked about are the integral test and the comparison test. Neither of those are applicable in this type of example, though. The reason is because, remember, there are requirements for the integral test and the comparison test. The requirement for the comparison test is that all the terms have to be positive, and they're automatically not in this case. These are about alternating signs. And so the comparison test is not applicable. And also the integral test is not going to work because the integral test requires that the function itself be decreasing. And this thing, these series that we're talking about, because of this alternation, they actually don't even make real valued functions. You can't turn this into a real valued function, -1 to the power x, because -1 to the power x is not a real value. It's not a continuous real function. So neither of those will work. I say use a different method. Typically, what is required here is we will use the fact that if some series converges, then this is something that we talked about quite a while ago, like at the very beginning of talking about series. This is a true fact about series. If the series converges, then that means that the limit of the absolute value of the terms must be 0. This is a basic fact. If those terms themselves are not getting really small, that is going to 0, then this series definitely diverges. It like becomes infinite or something. If those terms are not becoming really small, then the series can't possibly converge. All right. How would you show this to demonstrate something diverges? Actually, this is the same as, I'm going to write this kind of the other way around. This says if it converges, then this limit is 0. What that means is if that limit is not 0, then it definitely does not converge. So this is the same as saying if the lim of the absolute value an is not 0, then it diverges. And that is fairly easy to work with. All right. If the limit of the absolute values is not 0, then it diverges. That is saying the same thing as what I said the first time, just sort of the other way around. So, for example, here's one which diverges. How about show that this one diverges, -1 to the n. This is the same as the previous example. Well, not exactly the same. It's very similar. Show that this one diverges, all right? Since I want you to show it diverges, you cannot use the comparison, or I mean, you cannot use the alternating series test. That's only to show that something converges. But we can use what I said up here. If the limit of the absolute values is not 0, then it diverges. So that's what I'm going to demonstrate. I'm going to show that the limit of the absolute values is not 0. All right, so we'll show lim absolute value an is not 0. All right, and the absolute value is very convenient for us because taking the absolute value of this will kill the alternating sign, and then everything becomes a lot easier to understand. So in this case, lim n goes to infinity, absolute value an. An is just the entire thing, right? This part without the sign we call the bn, but here I'm talking about the whole thing. So the absolute value of the ans is, well, let me just write out, it's the absolute value -1 to the n times the other part, 2n plus 1. The effect of those absolute values, though, like I said, is just to kill the -1 to the n part. Because these are alternating in sign. Some of them are positive, some of them are negative. but when you take the absolute value, they all become positive. So the effect of this absolute value sign is just to get rid of the minus sign, which is great. And now what is that limit? Again, we use sort of ordinary methods for finding limits. You could do L'Hopital's rule, or you could just divide through everything by n. I'll divide through everything by n. It says 3 minus 1 over n, 2 plus 1 over n. This becomes 3/2. And this is not 0, so it diverges. All right? So this is how you handle showing that something diverges. You cannot just use the alternating series test, because that's only about convergence. All right, instead do this thing. You'll have some more practice with those on the homework. I don't think we need to do another example like that. Right, great. Let's talk about, I think we got enough time to start talking about the next section. This was the alternating series test. It's, like I said before, it's fairly straightforward. I mean, the idea of it, it's just a matter of not screwing up the execution when you, especially showing the decreasing part, is a little tricky to not mess it up, but there's not a whole lot of ideas to it. All right, great. Let's talk about, this will be the next section, absolute convergence. And it's vaguely related to what we've been talking about so far today about alternating business. It has to do with telling the difference between, or being careful about the difference between alternating signs versus not alternating signs. So remember, this is something I already sort of drew your attention to once today, but this is called the alternating harmonic series. This converges, but if I make them all positive, it diverges. All right. There's actually a word for that. The fact that this is a series where by itself it converges, but when you take the absolute values, it does not converge. All right. So here is, I'll write this as a definition. So here's a formal definition. It says if some series, well, if I'm looking at a series like this, if the series of the absolute values converges, we say the original series, AN, is absolutely convergent. And the word absolutely in this case refers to absolute values. All right, it's not just like an emphasis term. Absolutely convergent means that it converges even if you take the absolute values. All right, that's different from saying the original thing converges. When I say it absolutely converges, it means when I take the absolute values, it converges. All right. So that's what this word absolutely convergence means. So if, and there's a related term here, and this can happen sometimes, if AN converges, but the absolute value diverges, then it's not absolutely convergent, but it is convergent. So then in that case, we say the sum AN is conditionally convergent. Conditionally means like, okay, yes, it converges, but only without the absolute values. All right, that's what it means to be conditionally convergent. All right. And so an example of that would be something like, 1 minus a half plus a third minus a fourth plus etc. This one is conditionally convergent. conditionally. That is to say, it converges, but if you were to take the absolute values, it would diverge. That's what conditionally convergent means. It converges, but if you took the absolute values, then it would diverge. All right. So it is possible, like in this example here, sometimes with the minus signs it converges, but when you take the absolute values it diverges. Actually, and you might wonder, is it possible for the other way to be true? Can it be that this one converges but the original one diverges? Actually, that is not true. That's not possible. And that's what I wanted to talk about. I have sort of this, I'm going to write this as a theorem, and then I want to do one example, and that should do it for today. This situation, it can be the case that the original series converges, but the absolute series diverges. The other way around cannot be true. That's because if the absolute one converges, automatically the original one converges. That's what the theorem says. It says if the sum absolute value an converges, then automatically the original one converges. The sum an converges. The basic idea here is just that the if you think of converging means it adds up to like a specific number, whereas diverging means sort of it goes to infinity or something like that. The basic idea is this one is bigger than that one, right? When you take the absolute values, maybe it's the same, or maybe some things which used to be negative have become positive. This one should be bigger than that one. And that means that if this one converges, then this one should also converge by this, like the comparison test, right? If you have a bigger and a smaller, and the bigger one is converging, then the smaller one also converges. Now, what I just said, that actually is not entirely true. Oh, they tell me this every day. Not now, is what I say every day. My iCloud is full, but I'm not paying the 99 cents or whatever to get the extra 10 gigabytes or whatever it is. No deal, Apple. Anyway, what was I saying? Yeah, this is bigger than that. And so that's why you should feel on an informal level, if the bigger one converges, then the smaller one should also converge. This is not technically a valid argument because these are not always positive. I'm not assuming that they're always positive, and in fact, this is really only interesting when some of these are negative. So you can't use the comparison test because they're not always positive. But here's a little trick for this. So I want to talk about the real deal. It does involve the comparison test, but you got to do a little funny business first, which I think is kind of cute, which is why I wanted to talk about it. Check it out. Consider the sum of an plus absolute value an. All right, I am instead going to consider this thing and think about what actually are those numbers. When you add one number plus its own absolute value, what is the answer when you add one number plus its own absolute value? I would say if the number is positive already, then you're just adding these up and you just get 2 times an, right? If you have one positive number and you're just adding it to itself, you get 2 times whatever that number is. Or what if this number was negative to begin with? Then you're taking a negative number and adding its own absolute value, which is the positive version of that same number. They will cancel and you'll get 0. All right. So actually these terms here, each term here is either 0 or 2 times an. This is what I just said. If that number an is negative, then when you add its absolute value, they add up to 0. But if it was positive, then when you add its absolute value, they're the same number, and so you get 2 times an. All right? Each term is either 0 or it's 2 times an. So one thing we can say about this here, all terms are greater or equal to 0, right? Because each term is either 0 or 2 times an when an was positive. So that means we can use the comparison test on that thing. So we can use the comparison test on that series, all right? The comparison test does not apply directly to the original series because many of those terms may be negative, but it can apply to this weird thing, an plus the absolute value of an, all right? And what's the comparison we make? Our comparison is, compare like so, the sum an plus absolute value an. This really is less than or equal to the sum of 2an. That's because, 2 absolute value an. That's because this term individually, it's either 0 or it equals that. And so taking the 2an every time is going to be bigger than taking these ones, because these will be the same, it's just some of those are 0. All right? So here I'm taking the biggest possible answer that you could get. The answer is either 0 or 2an. All right? And this on the right-hand side, of course, we can factor the 2 out. This is the same as 2 sum absolute value an. And this, as part of the theorem, we assumed that this converges because the statement of the theorem says if this sum of the absolute values converges, then the other one converges. So we assume that this converges. That means by the comparison test, this one also converges. So by the comparison test, this one on the left side also converges. Sum an plus absolute value an converges. And it actually adds up to something. So this is less than 2 sum absolute value an. And now we can do some business. Now that we know that it converges, you can split up the sum on the left side. So that means the sum an plus the sum absolute value an is less than or equal to 2 times the sum absolute value an. And now I can just subtract this over on the other side, and it will say the sum an less than or equal to 2, not 2, sum absolute value an. So that means that the sum an also converges. That was the point of what we were trying to show here. All right. Cute little trick about adding the absolute value into there. All right. So the moral of the story is, if the absolute value version converges, then the original one also must converge. All right. And this is actually a useful fact. I wanted to just do one example, and then I think that'll do it for today. We'll do some more of these next time. But we can use that fact to do things. How about something like show that this converges, sine n over n squared converges. All right. This one is very similar to ones that you can do with the comparison test. These ones you probably did some, we did some in class last week, some you may encounter on the homework, where you do the comparison test and you say sine of n is always less than 1, and so you can just sort of replace that with a 1. The problem is this sine of n is often negative, and you can't do the comparison test when the things inside here are negative. So I'm going to say the problem, like what makes this not just the same as one that we did last week, I will just say you can't directly use the comparison test. Since sine of n is often negative. So sine of n over n squared is sometimes negative. And remember, the comparison test only works when all the terms are positive. So you cannot directly use the comparison test because that thing is sometimes negative. But we can use the theorem that I just said. The theorem says if the absolute value version converges, then the original one also converges. And that we can take the absolute values and then they will be always positive. So instead, we look at the sum absolute value an. And then if that converges, then it means that the original thing also converges. All right? So what is this? That would be the sum absolute value sine n over n squared. Now the absolute values don't really simplify much. So you can say the absolute values of a fraction is the same as absolute value on the bottom and absolute value on the top. So I can do that. This is the same as absolute value on top divided by absolute value on the bottom. And actually, n squared is already positive, right? So the absolute value can be thrown away on the bottom because the bottom is already positive. The top is sometimes positive, sometimes negative, all right? But now, anyway, now we use the comparison test. Because these things are all positive, right? The absolute values make it so that they are all positive. And what is the comparison? I hope you recall the typical thing to do in the comparison test would be to compare with 1 over n squared, right? You just throw away the sign. The sign is always less than or equal to 1. And so I am increasing the numerator to 1. And then what about sum of 1 over n squared? Does this converge or diverge? Anybody remember your things about series? This is some kind of series. What kind of series is it? Yeah? It is a p series, yeah. And does it converge or not? Yes, it converges because the p is 2, which is greater than 1. That's the rule. So this is a p series. P is greater than 1. Some kids just walked by. They heard me say P. Wonder if they thought that was funny. This is a P series, P greater than 1, so it converges. All right, and so that means the series that I was talking about before, the one with the absolute values, so this converges, and so by the theorem, the thing without the absolute values converges. By the theorem that we just talked about, right? The theorem says if the absolute value one converges, then the one without the absolute values converges. And this is the point of this theorem. It's so that you can use comparison tests in certain situations when the things are not all positive. You just pretend like they were all positive by taking the absolute values. All right. And this, I think, is all that I wanted to do today. I know we got 10 more minutes, but we're going to do some more examples of this next time, if you don't mind.